Okay. Welcome to the fifth lecture of Power System Stability. In the previous lecture, we have studied about a single machine connected to infinite bus and the concept of power angle, synchronizing power and synchronizing torque. When a disturbance happens to such a machine which is connected to grid. Now in this lecture, we are going to study multiple machines. We are going to study the analysis for multiple machines connected to the system and if they operate in unison, and then if a disturbance happens, how will we model the stability of such a system. So in the previous lecture we had equation 15 derived as m per unit into d squared del by dt squared equals Pm minus Pe. Pm minus Pe. This is your Pa, which is accelerating power. This is mechanical power. This is electrical power. Okay. Now this M can be written as H divided by pi F, and if it is a single machine, this is the H machine. H machine. Okay. Now, if you multiply the LHS and RHS of this equation with G machine, then you get G machine into H machine divided by pi F into d squared del by dt squared equals Pa into G machine. Okay, this is Pm minus Pe. Okay, this is Pm minus Pe. Now we can write G machine by G system. What is G system? See, G machine is the three-phase MVA rating of the machine, which is taken as a reference or the base. Okay. Now, if multiple machines are there, we need a G base or G system base to convert all parameters to per unit. So that is what is G system. Okay. So basically your G machine equals machine rating base, and your G system equals system base. Okay, so this can be written as this is let this be 1 minute. Okay, G machine by G system into H machine by pi F. We are multiplying with LHS and RHS by G machine here. LHS and RHS by G machine. So G machine by G system into H machine by pi F into d squared del by dt squared equals Pm minus Pe into G machine divided by G system. Okay. Now this can be equation 16. So in the previous lecture, the last equation was equation 15, which was the swing equation for a single machine connected to infinite bus. Now let this one G machine into H machine by G system. This part. G machine into H machine by G system. Let this be H system. Then we can write this as H system in the sense machine inertia constant on system base. Machine inertia constant on system base, because we have on the denominator G system, right? So machine inertia constant on system base. So this can be written as, this equation 16 can be written as H system divided by pi f into d squared del by dt squared equals Pm minus, now I am making it small m, Pm minus Pe per unit. Okay, on system base. On system base, because RHS here in equation 16 was Pm minus Pe into G machine by G system. So when this was multiplied with G machine by G system, this became per unit. Okay. Now here this can be equation 17. Equation 17. Okay. Now if these machines are swinging in unison, that means if multiple machines are there and if a disturbance happens, then some machines will accelerate and some other machines will decelerate. But the rate of acceleration and rate of deceleration will be at the same rate. I mean, will be same. The rate of acceleration and rate of deceleration will be same. That means the displacement of the physical rotor axis with respect to the reference magnetic axis for all the machines which are accelerating and all the machines which are decelerating will be the same, right? So in that case, for simplicity, we can start with 2 machines and later we'll move on to n number of machines as a conglomerate. Okay, so in that case, we have first machine. For the first machine, let it be h1 by pi f. h1 by pi f into d squared del 1 by dt squared equals Pm1 minus Pe1. Let it be equation 18. Similar to this, we are going for the second machine. For the second machine, h2 by pi f into d squared del 2 by dt squared equals Pm2 minus Pe2. Let it be equation 19. Now we have already seen that the rotors swing in unison. That means the displacement is same, which means del 1 can be equal to del 2 equal to del. So adding equation 18 and 19, if you add equations 18 and 19, what you get is, 1 minute, let me increase the thickness. Okay. If you add equation 18 and 19, 18 plus 19 implies this will become H equivalent divided by pi f into d squared del by dt squared equals Pm minus Pe. So this is equation 20. Now what is H equivalent here? H equivalent equals 2 machines are there, right? So G1 machine divided by G system, then into H1 machine, right? Plus G2 machine divided by G system into H2 machine. 1 minute. H2 machine. Okay, so let it be equation 21. Okay, now if you have multiple machines with G1, H1, G2, H2, etc., Gn, Hn, then what about H equivalent? H equivalent equals, here it is, in this case it is G1 H1 by G system plus G2 H2 by G system, that is G1 H1 plus G2 H2 by G system. So for n machines it is G1 H1 plus G2H2 plus etc. plus GNHN divided by G system. G system. Okay. Now with this, that means now you are able to write the swing equation for multiple machines with system base. Now we'll see some problems to learn the concept in detail. Thank you.